and welcome to Climate Chat. I am your host, Dan Miller, with my co host, Leon Simons. I'm coming to you from California, and Leon's coming from the Netherlands. So we're covering the globe here. And today we're going to be doing, like, in a sense, a summary and revisiting some information because it's so important. And actually, I was in Washington, D.C. last week meeting with some people, including some high-level people in government and related things that deal with climate. And and then some other people, too, that are in academia and things like that, talking about climate. And I can say that the stuff we're talking about here today, even though if you're listening to the show over and over again, you know it and you understand where it comes from, but this is not well known. The idea that warming is happening faster than the IPCC predicts, not well known at all. And that's a big problem because we should be dealing with reality rather than fantasy. In fact, the COP30 meeting just is finishing up, and nothing much happened there. And I guess part of it can be that if you can just ignore what's really happening, it's easy to kind of focus on other things. So Leon Simons has done great work putting together data from real sources. Like, this is like from satellites that are actually measuring the energy flows on the Earth, and then comparing it, looking at things like what's the real impact of aerosols or fine, like, smoke particles that we emit when we burn fossil fuels, and that helps reflect the sun away, helps create clouds that reflect the sun away. So that thing has an impact in cooling the planet, and that has not been studied well. Leon's probably done the most work on that, actually, if anyone. And he also worked with Jim Hansen on a famous paper, Global Warming in the Pipeline, where they took a look at how much warming you get from the greenhouse gases we've already emitted and the ones we're going to emit. And they found out that, well, they concluded that there's going to be more warming than is generally assumed. And you combine those two things together, that there's more cooling from aerosols than we thought, and there's going to be more warming from the greenhouse gases than we thought. And that's a recipe for living in interesting times, as the curse goes. May you live in interesting times. So with that general background, Leon, welcome. Great to have you here. And what kind of data? Oh, should we start off with what the three truths are at the high level?
Yeah, let's. I have them here in my slides. Where is it?
Oh, okay, you want to pop that up then, or
is it this one?
Let's see. Your Leon's.
Yes. Yeah. So indeed, like, we call this the 3 climate truths everyone must know, and here they are, and they're just not just about climate, but very much climate related, of course. And the first one is that the climate is changing faster than most realize, and you already elaborated a bit on that. And the second one is clean and affordable technology can lift billions out of energy poverty. And yeah, and then the third one is it's still possible to avoid the worst climate impacts. I think it's useful to discuss these three, and I mainly have some slides on the first, but I also have quite some expertise on the other points. So I think it will be interesting to just talk about it and see what we can learn from that, because I think these are really crucial, right? And Bill Gates put out a letter, I think, what is last month, and many have been communicating, of course, about climate change the past months because of the Conference of Parties in Brazil. It's more on the agenda again, and what we see, what I really noticed the past month is that there's a lot of there's like two things happening. One is that there's like general agreement now that we have or are or will soon pass 1.5 degrees of warming, which was agreed 10 years ago, the Paris Agreement. And on the other hand, there's this narrative that which is in a way it's always like added to this statement. It's like that we've avoided the worst, and I think that's really a strange way to frame it, right? It's like, okay, we cross this boundary which we said we really shouldn't cross, and then but we've avoided the worst, and then the question is, what does the worst mean? If the worst means that like continuing these extreme levels of CO2 emissions for the next 75 years until 2100, and that will have some certain climate impacts. Yeah, I think that if you make the worst case bad enough, you always have you can always say you did better than the worst, right? So to me, that doesn't really mean anything, and as I think we should just go into it and then at the moment we are following even a path that is worse than the worst.
So one thing we'll do is, as you go through the data, I'm sort of going to act like an interested student who's not that well versed in climate, because some of these charts are complicated. I'm going to try to ask questions as if I'm sort of a viewer that's not as up on everything, to try to make them more understandable. So let's get into it.
Yeah. So let's go back, I think, to 1972 when the Club of Rome, and I'm a member of the Dutch chapter of the Club of Rome, and published this report, and it got quite a lot of attention. It was the report was called "The Limits to Growth," and it was mainly about exponential growth, about what, of course, the economy and the world energy use and pollution and the population of the world were really growing at an exponential rate at the time. And what they did was they modeled, and they on the first computers they looked at what happens if we keep going like this, right? So it's like the first really like these scenario models which are now used very widely, also to base climate models on. And this is a graph that's included there in the 1972 report, where they said they showed these Mauna Loa these measurements of CO2, and they extrapolated this exponentially. And then I plotted the measurements from Mauna Loa to up to date, and they can see that it's like, of course, here there's a bit of a dip here, and that's because of a volcano. Mount Pinatubo cooled the oceans a bit, and the oceans absorb more CO2. But it's like it's kept really growing, not exponentially, but really at a very large rate. And we are now all the way here at about 427 parts per million. So of course, that's what we always talk, especially what's really talked about mainly also in these COP meetings, but also in these scenarios and these what are the carbon budgets, and then people mostly talk about CO2.
But just to give some context on this for everyone who might not be as familiar. So we're talking about a concentration of CO2 in the atmosphere, which in pre-industrial times was about 280 parts per million, or 0.028% of the atmosphere was CO2. And now it's about 427, which is 50% higher, at around 0.042% of the atmosphere. Now, that doesn't sound like a lot. It seems like a small number, 0.04%. But you have to remember that most of the atmosphere is nitrogen and oxygen, and they don't absorb heat radiation. So they're irrelevant to the whole discussion. It's only the part that does trap heat that matters. And it turns out that there used to be around 2 trillion tons of CO2 in the atmosphere, and now it's closer to 3 trillion tons. So that's a lot of greenhouse gases, and that doesn't include methane and nitrous oxide and the other greenhouse gases that also trap heat.
If you include those, we have practically more than doubled the concentration of CO2.
But if you were just if you're just looking at it and say, hey, I want to do an experiment, let's increase the CO2 content of the atmosphere by 50% to see what happens, everyone would think you're an absolute nutcase and would lock you up or something, for having such a crazy idea, because of how dangerous that would be to alter the atmosphere, increase CO2 by 50%, because we've known it's a greenhouse gas for a long time, since the 1800s. And yet that's exactly what we're doing. We're doing it without any thought, without any planning, without any thought of what this means. We now even know what it means, and yet we continue doing it as if there's no other choice. So there you go.
Yeah, and then I think it's also, this is quite a
this wasn't hard to see. But I can zoom in on it maybe, but
yeah, I'll zoom in on one part later. But I think it's important to highlight that what I just talked about, that you have all these statements that we will keep warming, as Bill Gates framed it. It's and that's what he built his whole letter on, where he I'm paraphrasing a bit here, but he says he was like, we shouldn't make climate more important than health, and we should focus more on health, solving health problems in developing countries than reducing global warming. And of course, that's it's not a zero-sum game, and I think it's quite ridiculous to frame it in a way that it's like either we are killing children in Africa or we are solving climate change, right? That's like, in a way, it feels almost like you're blaming the children in Africa for not solving climate change. But then even then what he built this whole narrative on that we're doing. He said we're doing well on climate change, even if we don't do much. If we I don't know exact wording he used, but even if we don't do much more than we're doing now, then we'll keep warming, global warming, this century below 3 degrees Celsius, and that's really wrong. And he said that it's the consensus, but the consensus really isn't that. An important reason, I think, why he thinks that. Of course, he's not a climate scientist, and he doesn't really understand, I think, what's behind these models and these scenarios that he uses to make these statements. But why he thinks that is, I think, because many of these scenarios, and there's United Nations Environmental Program published a paper on this where they made a similar statement, and UNEP and the Climate Action Tracker is what he referenced, where they say, okay, we have this much carbon budget left, and it seems like we're doing better than if after Paris we've been doing better. But what it doesn't talk about, if you look at these scenarios, and it's really hard, even for me and even for experts who should really know what's behind these models and what the underlying assumptions are to come up with these statements about 2100. It's really hard to understand what the underlying assumptions are. And even in the updated IPCC report, these climate indicator reports they've published every year now, they mention here, and this is really important. So you have the CO2 and the other greenhouse gases, but the emissions in the future, they are not made available. So the assumptions they make about non-CO2 emissions, so that's methane, nitrous oxide, and of course aerosols, they are not transparently given. So we really don't know what their assumptions are, underlying assumptions are, to make these kind of statements. And that's then I get to this graph, and I've showed this here before. There's a lot going on here, but I think it's important to go through it, because these are the greenhouse gas forcing. So a forcing is what, in a way, forces the climate to change, and it uses the unit watts per square meter. And this so these are years since 1850, and then at the top in gray you see the greenhouse gases, and of course the emissions of greenhouse gases have been increasing over the years, and then you see also the rate of greenhouse gas forcing increased. It hasn't increased much because there's a logarithmic effect. So, but the net forcing is very much determined also by the cooling effect of aerosols, of air pollution. And we talked about that more often here as well. But the assumptions you use for that, and there's very big uncertainty, that's the biggest uncertainty in climate science, is how much warming has been hidden in a way by air pollution, and it's mainly sulfur air pollution. And the sulfur is part of the fossil fuels. If you burn these fossil fuels, the sulfur comes in the air, it reflects sunlight, and it makes clouds brighter, which also reflect more sunlight. And then, so with the burning of these fossil fuels, there was not just warm, but also cooling, a negative forcing. So which made the net forcing, the sum of the greenhouse gases and the aerosols, made it lower than just the greenhouse gas, of course.
Oh, sorry.
And
sorry about it.
But because it's extremely uncertain, we cannot just use models, climate models we cannot just rely on climate models. Even leaving apart what the underlying assumptions are for the future, even for the past, we don't know the aerosol forcing. It's the biggest unknown in climate science. That's why James Hansen and his colleagues, including me, we took this reduction in aerosol emissions, or the sulfur emissions over the oceans from shipping in 2020 as an experiment. We saw that this was the biggest experiment ever, inadvertent experiment that we could use to reduce this enormous uncertainty of the aerosol forcing. And then what we saw, looking mainly also at satellite data, and of course we use more lines of evidence, but when we look at satellite data, we see an enormous increase, this is here in black, in absorbed solar radiation. So in 20 years, there was an increase in absorbed solar radiation of about 1.7 watts per square meter. So and that's on average, again, over the 510 trillion square meters of the Earth's surface. So the Earth is absorbing much more sunlight, really an enormous amount of sunlight. But it's radiating more heat to space. Of course, the Earth heats up. Greenhouse gas keep more heat in, but when the Earth heats up a lot, then of course also the outgoing radiation increases. So that compensated a bit for this enormous increase in absorbed solar radiation, but not fully. So that's why we have an Earth's energy imbalance increase. So how much heat accumulates globally on average, and then watts per square meter is a joule per second per square meter. So that's a lot of heat accumulating globally, and much more. That's an increase of about 1 watt per square meter. So from 0.4 to 1.4 watts per square meter. So and we conclude that this, and the recent paper this year published by James Hansen and colleagues estimates that's about half a watt. So half a watt of this increase is from reduction in shipping emissions, not just from 2020 onwards, but also before that, from regional regulations. And you really see that there's an enormous difference between the best estimate from the IPCC methodology and if you take into account this strong forcing from Hansen et al. And then of course, this difference in negative forcing translates also to the net forcing increase.
So,
because
yeah, I'm going to ask you let's go through each and every line here, so everyone can understand what's going on. The top line, and maybe you can point because I don't have the pointer on.
Yeah, here.
Yeah, that gray line is total greenhouse gas forcing. So that includes CO2 and methane and all of that stuff. Is that based on a model, or that's not measured, is it? Because there is no measurement of that alone, is it?
Yeah, that's based on the best estimate of the IPCC on these different forcing agents. So, and
Okay.
that's
So it's a
of
model,
course,
the IPC model based on how much, and we do have measurements of how much greenhouse gases are in the atmosphere. We know
exactly.
that. But now,
Yeah,
why isn't there
except for tropospheric ozone.
Mhm.
That's because so what you often see is these well mixed greenhouse gases.
Yeah.
Because those are the greenhouse gases that we can measure effectively globally. So you have these measuring stations around the world where they,
Mhm.
in a way, they just take a glass bottle and they capture the air, and then
Sure.
they measure the air, and to look at how much of these different gases is inside that pocket of air at a certain time of the year, right?
Okay.
And then you can see this growth rate.
But let's go on. Well, I have a question for you though. Since
Yeah.
that, I assume they're assuming a equilibrium climate sensitivity of 3 degrees on average for calculating the given a certain amount of greenhouse gassing, how much forcing will there be? It's based on a model, right? As you said, and I'm assuming their model is a 3-degree model, but
Yeah, but that's feedback. So now you're confusing feedbacks and forcings. So a forcing is what forced the climate to change.
right.
Then you have feedbacks that determine what the change is from that given forcing.
Okay. So
The
with your paper, Global Warming the Pipeline, which you did with Jim Hansen, and
Yeah.
you're coming up with an ECS of 4.5 instead of 3, you're saying the forcing, the original forcing, just directly from the greenhouse gases, you agree with the IPCC on that. It's just that the feedbacks are going to be stronger than what they
Yeah, so we looked at a different we looked at different at the greenhouse gas forcing in different ways, and we came we presented it also in the paper, and we showed that we get the same order of magnitude forcing from these greenhouse gases.
Okay.
So that's
All right, but let's
the
keep going
difference is
down
not
the
in,
lines.
but the difference is in the aerosols. So how much
Right. Well, I want to get to
of the
that. So now you have 2 lines below that line. One is they're both net greenhouse gases plus aerosol forcing. So if you go to the bottom, the yellow and the green, 2 different lines. One, the yellow one is the IPCC assumed cooling because it's below 0, right? It's a forcing that cools the Earth, and both of those are
it's
below
a negative
0.
forcing. So it
Negative
like
forcing, so it's cooling. The yellow one shows less cooling than the green one, and the green one is what you and Hansen and others think is the right number. That, in other words, that aerosol cooling is a bigger impact than what the IPCC says. So
and the
then you
best
take
estimate of
those
the
2.
IPCC. I think that's important to know that it's there's a big uncertainty range, of course, because every aerosol expert agrees that there's an enormous uncertainty.
Yeah.
So the uncertainty is given, but we estimate based on these observations mainly that
Right.
the aerosol forcing is much stronger. So
I'm not even trying to get into why we know all this. I'm just trying what the lines mean. So we have a yellow and a green line, and then when you subtract the yellow line from the top gray line, you get that brownish line there of net greenhouse but aerosol forcing, and then
technically you add it. You add the gray
that's
to
true. That's
the
true. You
yellow to
add
the
it,
gray. You add
and then you
negative
add the green
both.
to the gray, and you get the purple line, and that is showing really less net forcing until recently, when the ships were emissions were turned off, and then we warmed very dramatically at that point. Okay, so that's still calculated, really, right? Calculated and modeled numbers. Then we have the lines in the middle that start right after 2000, right? That's when satellites were turned on, Ceres satellite in particular. Then we have the black line, absorbed solar radiation. This is how much energy the Earth is absorbing.
Yeah,
And
these
we
are
see it
4-year
going
averages.
up rapidly. And the one thing that would make it happen is that the Earth is getting dimmer, is getting less reflective. And
that's how it happens.
Yeah, right. And so,
of course, you can have more sunshine, but that's really the order of magnitude is of changes in sunshine, especially if you take the 4-year average, is really almost negligible compared to this enormous increase.
Right. The sun has a 11-year cycle, and yeah.
It's about 2.2 watts or something.
Then there's outgoing. Then there's the red line, I guess. Outgoing. Maybe you could point to it, by the way, so people can see what we're talking about. The red line, and then that is how much energy the Earth is giving off, and that is direct. The biggest factor of all of that is as the Earth gets hotter, it gives off more heat or more energy. It radiates it out to space at
because it's going down.
The temperature in Kelvin.
It's going down here, but if you look at it at Earth from space, you see more infrared radiation coming from Earth.
Yeah, Earth would look hotter from space, but that means it's getting cooler. That part of it is making the Earth cooler. That's a really good thing. That's what helps regulate the temperature on Earth. As it heats up, it gives off more energy out to space, and it does it at the 4th power of the temperature in degrees Kelvin. It's not, I guess it's just Kelvin, not degrees Kelvin. But and so that's the regulation of the Earth. That's great. And then you have this yellowish line or orange line, I guess, in the middle, Earth energy imbalance, which is, I assume, the difference between the two, right? Of how much energy is coming in versus how much energy is going out.
Exactly. But so this is the absolute value, the orange. That's the absolute value, and that's like anchored to the global ocean heat content, mainly data. And these are the anomalies from the start of the observation. So if you see here plus 1.7, and this is minus 0.7, of course, and the year is 0.4, and if you add this and this together, and you get of course, so is only 1 watt per square meter more, and then you have this number. So it increases by about 1 watt per square meter because of the increase, mainly because of the increase, of course, in absorbed solar radiation. And then some skeptics, they say, okay, so that proves that it's not the greenhouse gases. But of course, without this increase in greenhouse gases over this period, right? You see, that's also almost, I think, about 1 watt over over 20-year time period, or 24-year time period. Then, of course, this red line would be much lower, and the energy imbalance wouldn't have increased if this wouldn't have grown. If the greenhouse gas forcing would have stabilized over this period, right? So you really have to take
there's still more than that going on, because the lines at the top, the gray and the purple and the whatever reddish one at the top, that indicates a forcing, and the bottom ones are a negative forcing or a cooling. But it's really the measured line, the absorbed solar radiation, is really the net effect of all of that. It's what, when you have more greenhouse gases trapping the heat, the absorbed solar radiation goes up. But as we also found out on Climate Chat, that the warming of the Earth also causes less clouds to reflect the sun away, which is a different factor than greenhouse gases trapping heat. And as you have less clouds, the Earth absorbs more heat, and that increases absorbed solar radiation. So it's not, in a sense, just the greenhouse gases doing the job. It's how the greenhouse gases warming is changing the Earth system to allow more energy to enter the Earth, as well. And actually, the greenhouse gases is really on the red line. It's trapping the heat, trying to get out. So anyway, there's a lot going on in this graph, and it's just confusing just to look at it. And I thought it might be worthwhile. Of course, we might have bored a lot of people already, but I just wanted to go through each line and give some more nuance to what's really happening here, because this graph here shows what's happening to the Earth right now in the highest level. That's why we should be really worried, because that orange line is going up. It is the orange line going up which causes the Earth to warm up. Everything else is sort of contributing to that orange line.
If the orange line was stable, the Earth would still warm up. But as it's increasing, it's warming faster.
Right. As long as the orange line is above 0, it means there's something. It's almost like, you know, you have a pot of water, and if it's 0, the stove is turned off, and at any time that there's a flame turned on under the pot, you're going to warm up that water, and that's any orange line above 0. And as the line goes up and to the right, it's like we're turning the stove up and making it hotter to boil the water faster. And so
until a balance is reached where when the water starts to evaporate, or the more heat is radiated from the pan, right? So it depends a bit on how you put your flame. But then, of course, you can reach a new balance from the feedbacks. So the feedbacks are evaporation of water and conductivity and radiation. So these are it's really basic thermodynamics.
Right, but that would be the black line and the red line canceling each other out. Then the orange line, the energy imbalance, would be 0, and the water or the Earth would stop getting warmer. So that's what we're dealing with here. We're allowing the Earth to absorb more solar radiation, and we're also causing it to block outgoing radiation. Those two things are happening, and that's why the energy imbalance is going up. And this is, by the way, this is so let me ask you, is there doubt about the Ceres data? Do people doubt its accuracy? That just the middle three, the absorbed solar radiation, Earth energy imbalance, and the outgoing energy amount emissions.
I think there was some.
Are there climate scientists that say, "Oh, I don't believe that stuff"?
Of course, there was some outspoken skeptics that were using a single cherry-pick database, which was their own, saying, "I don't see any acceleration in global heat uptake." But later, their data set was updated and did show acceleration. They never corrected their accusations that we were exaggerating and that NASA was exaggerating, that the data was incorrect. But that now their own data sets are in line with the NASA Ceres data set. So I think there's some skeptics. Of course, I think you see some skeptics saying, "Okay, this disproves." They don't say we don't believe in the data, but they say this data disproves that greenhouse gas cause global warming, which is, of course, very also quite ridiculous, because it's
no. I'm talking about the mainstream. I'm talking about the real climate scientists that are, you know, don't doubt climate at all, but yet they might have said, well, we think Jim Hansen's global warming and the pipeline paper is outside the mainstream. Let's say one of those kind of scientists. But then when you present them with this data measured from the Ceres satellite, they're not going to disagree with the data, right? But aren't they going to have trouble matching it up to their own beliefs of 3? You know,
I think what the responses, at least the response I've seen over the years, is it's natural variability. It's of course, if there is uncertainty in the data, we don't. Of course, we hope that it's wrong. We hope the data is wrong and that this effect is not that strong. But we do see now that, of course, the surface air temperature is increasing as well, and all the other indicators also showing these very strong increases. The global sea level rise is increasing. The level of CO2 in the atmosphere increased a lot because, of course, the forest fires increased. So there's many other indicators showing that there's more, the rate of heat accumulation in the Earth system is increasing faster.
Okay.
But we can go talk about these things longer. But I think it's
but I bet we hit it to death there. But yeah.
I think that if you compare this just from 2010 to, you know, because of course it really depends on on the scenarios you use, what kind of warming you expect. And then if you look at the SSPs, which are like these emission scenarios used to run these climate models, and then the updated methodology from Forster et al., and this is just greenhouse gas and aerosols again. You see again this forcing increase. This black dotted line is this growth rate, right? From these two, for the net effect of these two. And then this is again in red now what was pink there. Sorry, here. Then you see that this is now increase the increase if you trust the estimate of James Hansen, and it might be more feedbacks, but then the climate sensitivity is higher. So in a way that if it's not an aerosol forcing, it's more, and you take the data as a given, the NASA satellite data as a given, then the climate sensitivity is much higher, and it probably is both, right? So of course, this already takes into account the higher climate sensitivity, and otherwise the aerosol force would be much stronger even. So it doesn't.
This is also why you and Jim say that you predict that the rate of warming has gone up recently. So we were warming at 0.18 degrees Celsius per decade.
Yeah, I'll get to that.
And now you're saying it's going to double now. And that's because of that.
I just want to go back, to this point where, so to understand all these statements that we will keep warming below a certain level, I think it helps to understand what those assumptions are based on, and those are based really on what drives the climate to change, which are these forcing agents. So if you want to understand, you really have to understand this basic stuff. You cannot talk about climate change and about temperatures in 2100 if you don't understand what forces the climate to change. So, and these are the forcing agents. And if you look at it, then this shows why it's also crucial to take these aerosols into account. Because if you just look at the greenhouse gases, right here you see, here's the Hansen estimate with aerosols. So reducing aerosols, of course, leads to this big increase. And if you don't take that into account, which many don't, and some, of course, Climate Action Tracker, I don't have a clue. Nobody knows. Maybe, I hope they know, right? But nobody. I asked a lot, and I've been looking into this for years, but also for the past weeks after the Bill Gates made this statement, and everyone kept echoing this statement that from all these different bodies that we will keep warming, that there's some great news besides that we've passed 1.5, that will keep warming below 3 degrees, that there's some achievement because of Paris apparently, right? But nobody seems to know what the underlying assumptions are for these statements, and I think that's really dangerous in a way, right? If you don't know what the underlying assumptions are, you cannot make these statements. You cannot make them statements, or you cannot cover these statements in the media, and you cannot repeat them after the media covered them, right? But everyone is just making these statements based on these black boxes. No one knows what's going on inside. And then I think, here's the doing this, extrapolating this to 2100, and of course you see this enormous increase up. And that's the purple line, the SSP 8.5. And I think that was my point, that we can say, if you make the worst case bad enough, we might do better, right? And we don't know if we will do better. Of course, I don't think China will keep doubling its coal burning every decade or so, but still, something might happen. If you look at, for example, if you take into account the carbon sinks, we might not follow this emission pathway, but we might still follow this forcing trend, right? I don't think we will, but we might.
Well, I
But
think an important point is the RCP 8.5, the one that everyone says, thank God we're not following that path. That is a scenario of emissions. Like, we don't know how much emissions humans will emit in the future. It's up to us, right? Maybe we'll get rid of fossil fuels and lower them, or maybe we'll continue on the path we're on. But the difference is, even though we're hopefully not following the emissions pathway, we'll have less than that worst case amount of emissions. The forcing that comes from the emissions we are putting out is following that worst case projection.
Exactly.
And that's something
this is in a way the same,
know.
right? If you look at this, right, we are still following it in a way. Of course, we talked about why these black dots are a bit lower, because of the IPCC methodology pretends like all these aerosols from forest fires in Canada are anthropogenic and causing cooling. Well, they of course are not. So, but if you look at if you take into account the greenhouse gas forcing, I think we really might indeed follow it for now. And if you look at the data, which of course we did, if you look at the NASA satellite data and the other lines of evidence, it's very likely that we are the forcing increase, the recent forcing increase. So because aerosols were hiding more of the greenhouse gas forcing, the recent increase is much higher, which of course also explains, or one of the conclusions that is then that also the climate sensitivity has to be higher. But then the warming we see over the next decades is of course determined by the current forcing, not by the forcing here, right? Even like what happens after in 2070, it's based on these forcings, right? That doesn't matter much for the impacts of the coming decades, of course, because those are determined by the current forcing increase and the current rate of warming, and the rate of change is what causes the risks, as we talked about many times here. So then, and then just to show you here, methane is also quite following one of the higher ranges of these emissions. So again, what do the climate models assume, right? What do these statements of Bill Gates or whoever, what are the underlying assumptions for methane? As I understand it, they all assume that methane is decreasing fast, quite fast. So that while we are now about here, right, that methane is now, it keeps increasing. So we are now above the level, for example, with methane, of the middle, like the middle pathway, the business, in some which some call business as usual. We're already at the peak level, and we're still growing.
I want to point out that
that number, limiting warming to 3 degrees. That's this line, right? This is the median of these models, and we're now above that, well above that.
So that number, 1938 parts per billion, that's the same as 1.9 parts per million. So we measure CO2 in parts per million. So we have currently, it went from pre-industrial 280 to now 427. Methane went from pre-industrial 0.07 parts per million to about 1.9 parts per million. So it increased about 1.2 parts per million in so far. And that's, well, how could that be a problem? Well, it turns out methane is way more effective at trapping heat than CO2. And while it's in the atmosphere, it's about 120 times as effective. So even that 1.2 number translates to about 2/3 of the warming of the CO2 causes.
Yeah, if you want to make it more technical even. So this methane, these molecules are of course different shape than CO2. So they absorb a different wavelength of infrared radiation than CO2 absorbs or water absorbs. So there's these different gaps of infrared light. Of course, with visible light, radiation is visible light is also radiation. So you have in infrared light, you also have different colors, but of course we can't see those. With invisible light, we understand that the different wavelengths have different colors, but that the same happens in infrared, and different molecules absorb different wavelengths of infrared radiation.
Okay.
And especially within these what's called the water vapor window, so the range where water vapor doesn't absorb certain wavelengths of infrared, greenhouse gases, other greenhouse gases do. For example, the methane and CO2 absorb different wavelengths of infrared radiation. And then the earth warms, and then there's more water vapor, and the increase of water vapor also absorbs more radiation, which is called the water vapor feedback. So that increases the warming and compensates a bit for this enormous increase in outgoing long-range radiation from the warming of our planet. But that's
okay. Yeah. By the way, we're at 10:45, 10:46, so we should probably, since we have a lot to cover, but I want to stop and say here, please, if you're getting some value out of our programs here on Climate Chat, please like and subscribe, and you can hit the notification bell as well if you want to be notified when we put a new video up. But it's really important, because what we're trying to do here, we're not trying to become rich YouTubers by having cat videos or showing you the latest fashions or something like that. We're trying to spread the word on climate change, and we can do that more effectively if we reach more people. And the way we do that is by you subscribing and liking the videos, so that the algorithms spread them to more people, who can then like and subscribe and spread it even further. So we don't ask for this. I watch other YouTube videos, and man, they're asking like every 3 minutes. They're stopping the video to ask you to do that. But we don't do that enough here. But it is important. So please help us out. Please help out the cause, and by liking and subscribing and sharing the video with your friends if you think they might like it. Okay.
Okay. So yeah, I think we looked at it before, but fossil fuel CO2 keeps increasing. Let me go through it quickly. And sulfur emissions keep decreasing. These are global fossil fuel emissions, and there's a different way to show the data, and it's kind of plot again here. Fossil fuel, sulfur dioxide, and billion tons of CO2. And you see, we're really the emissions are decreasing, of sulfur are decreasing, and the emissions of CO2 are record high. And this is for shipping, and you see the same, right? You see, of course, there's a bit of a decrease from shipping, maybe more efficient engines, etc. But the enormous decrease here again, the enormous decrease of sulfur emissions from shipping, it's really this is really an enormous change. And here you can see CO2 increase further. So that if you keep looking at this data, you see many different things happening. For example, here you can wonder why CO2 increased more than sulfur did at the start of from 1850 to let's say 1950. And that's because it was mostly coal-fired shipping at the time. And now, of course, you see then they switch from coal to oil, and then there was relatively less CO2 being emitted, but still a lot of sulfur being emitted. So then they increase more or less linearly if you look at this, use these ranges.
So this is very confusing, but what's happening on the right chart is that basically as CO2 increased, SO2 increased, and kept going up and to the right, and then all of a sudden there was a rule change, and those little numbers they're shooting back to the from the upper right. They would have been part of the upper right, but because the rule change said, "Hey, reduce sulfur in your fuel," boom, the CO2 kept coming out of the fuel. And all of a sudden, the sulfur was 80% less. and that's why.
Yeah, so it's still like 0.8 billion tons of CO2 per year.
Okay.
But sulfur is much lower now. It's only 2.5 million tons from the peak of over 12.5, so 10 million tons higher, right?
Yeah.
Okay. So it was really, and those were mainly over the pristine oceans. And then, again, like I think we could talk about this longer, but so we really see the rate of warming increase. We see, and then we said, okay, the rate of heat uptake increase. Then we see the rate of, we said we will see the rate of warming of the surface air temperature increase already in 2022 when we published our preprint of the James Hansen et al. Paper. And then, of course, 2023 and 2024 happened, and we saw these like enormous peaks. And we expect this rate of warming to continue, and it might be even we might have even underestimated, right? If this, it could be worse. If you see there's some indication that the rate of warming, I think this line is 0.36, so a doubling of this line of the trend from 1750 to 2010. If you this is the extrapolation of that, and then so there was 0.18 degrees Celsius per decade. This is a doubling of that, but it could be, at least for now, it's about 0.4. You see this line is increasing now faster than this line is going up, right? So depends a bit what happens in the future. It's uncertain, but it could be even worse than we thought. And there's now a consensus over this acceleration, but that doesn't really translate into these predictions for 2100, right? So you see, for example, now in the Conference of Parties in Brazil, they more or less agreed that, okay, we should rely on the IPCC because that's like the most trustworthy scientific body. But the IPCC is always a decade or so behind, right? If you look at the data now, this is we see that there's acceleration. We see that there's acceleration of warming every day. There's many scientific studies coming out. But if you then use these computer models, these simple climate models, and pretend like that's the highest level of science, then you get to then you can make these statements about 2100 and even. But if the climate sensitivity is higher, then it's worse than these models, than these simple models show. I think that's really important. So maybe this one, the last. Let's finish with this one.
Yep.
Or like this. Again, so. We talk. You can watch our show on 3 degrees by 2050. How likely that is, and I think that the risk is so high that whether it's 1 or 5 or 10 or 20% likely that this will happen, it's not really even that relevant because the risk is so extremely high of 3 degrees, especially it happening by 2050. That we really should do everything in our power to make sure that it doesn't happen, and to adapt to this potential risk, right?
And even if it doesn't happen by 2050,
what are the chances of your
2060? If it doesn't happen by 2050, and it's still showing it's going to happen by 2060 or 2070,
exactly.
the latest.
But even then,
and it doesn't matter. I mean, it's all absolutely catastrophic. End of civilization kind of thing. So the risks are totally unacceptable, even if it's not quite as fast as it could happen. Even if it happens at more the steady pace, it's all within the lifetime of our children, and totally unacceptable. And by the way, it's not like you hit 3 degrees and all of a sudden everything starts going bad. I mean, things are 2 degrees is an utter catastrophe, and we're going to see that next decade. And if you think the current climate change is bad with the crazy floodings and the crazy extreme weather and the fires, and you don't like that, and the droughts by the way. Tehran may be running out of water any time now. They said they're going to have to abandon the city because of that in the long run. If you don't like that kind of thing, 2 degrees is way worse than that. And that we're not even at 3 yet, right? 3 is when you can't really adapt anymore. It's just food supplies are collapsing and things like that. So
yeah, but I think it's really important to show that these, like, if you put trust in NASA, if you put trust in these models, it's really important to note that might look technical, but I think it just simply, if you see this dot is higher than any of the models, this is the observation, these are the models, these are the models.
Why don't you zoom in on that chart, because that one's you can zoom in on the chart so people know what you're talking about. You can like zoom it in. At least I could. This. Oh, I can do it on mine. Okay, you can't do it on yours. Okay.
Yeah, people can let
me replace this one, and then let's see. Let me find it here. This one, right?
Yeah. So here you see that all these models are. So all the dots are models, and then the black dot with the uncertainty ranges are the scenarios. And I can talk about this for a long time, and I think we did before. But I think just to highlight, this is this shows that the Earth is absorbing much more sunlight than the models assumed, and also radiating a lot of
up in this direction is how much energy the Earth absorbs shortwave, and this direction is how much energy it's giving off long wave or heat, right? So things that are in this direction would be cooler, and things over here would be warmer, and that would be the model.
Energy. Sorry.
Yeah, that's the model, and this is the data point from the actual satellite saying, we're emitting less energy than the models say, and we're absorbing more energy than the models say, and that means the models are wrong in the wrong direction. In other words, it's more dangerous than the models are showing us.
Yeah, and of course, part of this can be explained likely by stronger aerosol forcing, but also likely by of course the stronger cloud feedback.
Right.
And it's very hard to disentangle those two, right? And it's also in a way it depends a bit on your definition of a forcing or your definition of a feedback, which is more of a scientific discussion. Here again, these SSPs, right? Those are the model, and then it seems extreme, 3 degrees by 2050, but I think it's hard to talk about risks, right? I think everyone in his personal life knows about risks. Like, for example, I think everyone can think of what one of the highest risks is in your country, right? Whether it's traffic or whether it's water. So we live in a country which is largely below sea level, with water everywhere. So what we do is we teach our kids to swim, right? And we teach them very young, and we go every week. We go to the swimming lessons, and I've been doing it now for 5 years with my 2 kids, and it takes a lot of time, and it's quite annoying. But you do it not because they will, for certain they will fall in the water when you're not around, and they will drown, right? You know that the risk is there. There's a risk, and you want them to be able, when they walk away and you don't see them, and they end up in the water, wherever, they will be able to get out of the water alive, right? So even if the chance of that happening is only 1%, it's still work. It's like you would never forgive yourself if you don't prepare yourself for this tangible risk. And I think in every country you have these environmental conditions, right, where you teach your kids like not to fall off a mountain, or to wear a helmet, or to whatever, I don't know, be safe around guns in countries where you're around guns all the time, right? So you need to prepare for these risks, and now we have a global risk of this extremely rapid climate change happening within DEC, and it's already happening. The rate is really, it's there based on observations.
Mm-hmm.
So
okay.
Yeah.
Well, one other chart which is related to this one is the one Jim Hansen published in his write-up. Do you have that one, the colorful chart that everyone's ignoring or that no one knows about? I could.
Yeah, I think it's inside my.
Okay.
My
Jim Hansen did something that he's continuing to follow up, doing what we're doing here, telling people that what the IPCC is saying about climate change isn't right. It's actually worse than that. And looking at he's looking at the charts of the real data, showing that warming is growing faster than everyone thinks, and trying to warn people about that. So we should maybe go on to. Oh, there it is. Okay, let's get. There we go.
Yeah, it's the same, right? These are forcings.
Mm-hmm.
These are greenhouse gas forcing. So annual increase in climate forcing by greenhouse gases. So we talked about this, and this is just the rate, the delta forcing equivalent of effective forcing. Sorry, in watts per square meter per year, and then it's like the growth, the annual growth rate of these forcings.
Now, people might ask, what is that red doing? And that actually are these chlorofluorocarbons.
Halogenic gases. So
and the Montreal Protocol to solve the ozone hole problem eliminated those, and that
this is like the most effective climate policy which was not about climate policy, right?
Yeah, it would have been way worse if we hadn't done that. But now we continue to grow. The blue down here, the bottom, the light blue is CO2, and then the dark blue is methane. And anyway, you add them all up, and you can see the forcing, not the emission scenario, but the forcing is following the worst case RCP 8.5.
Technically the rate of forcing increase, and if you would add, show also aerosols here, but then you have like the line is going like this because you have all these very variable aerosols, of course, and those change every year. So an annual aerosol change is not very informative. Do you still see me?
Yeah, yep, I still see you. Oh, wait, there's the other one there, but you want to show that other graph? Oh, I got to turn that one off. Okay, hold on.
I don't see my mouse moving, so that was a bit.
Oh, okay.
Yeah, and just to finish up with this one, we talked about this one about the North Pacific, and I just want to show this to highlight that the regional changes are much more extreme, and we see now the over this past 20-year period, the 4-year average level of absorbed solar radiation over the North Pacific Ocean increased by almost 5 watts per square meter, right? And there used to be this very strong correlation between the Pacific decadal oscillations, so this varying temperature regions in the Pacific, and the level of absorbed sunlight, and of course also on temperature. But this has really changed from 2020 onwards. So 2020 is when this sulfur mitigation policy came into effect. So again, these are observations. The Pacific Decadal Oscillation Index is based on observations, and the radiation is also based on observations. And then even, I think, when we talked about it, I think 2 months ago, about the North Pacific, these extreme sea surface temperatures, the data was 2.4 watts per square meter of net flux. So and now it's 0.2 of a watt more. And again, here, if you look at this is per decade, per year, you see the greenhouse gas forcing is not even 1/10 of a watt. So if the net flux keeps increasing, like by 1/10 of a watt in a month, right? To me, this is really worrying.
That's crazy.
And
although some of it is fluctuations, right? So hopefully,
it's but you see it growing, right? You see this growing
yeah,
faster
the
than this
lines
one.
are diverging. Mm-hmm.
The lines are diverging, which means the net flux is increasing, and these are 4-year averages. So
wow. You've already smoothed out a lot of the monthly or yearly variation.
There's much less variability because you have a 4-year average.
Wow.
And then again, this I think the PDO is also the 4-year average. So it's really like record low. Even if you look at the past 150 years, it's never been this low. So there's probably a correlation between the aerosols and the Pacific decadal oscillation. But if this turns positive, and that will translate to even more absorbed sunlight in this region, because there's still a lot of sunlight reflected over this region, right? The albedo, there's still a lot of clouds over the North Pacific. So there's still a lot of absorbed solar radiation increase possible if this region warms more and the clouds decrease further. And so this is really, I think, a really crucial region to look at. It seems remote. Most might think, okay, nobody lives there anyway, but this influences the climate of the entire Northern Hemisphere, right? If what happens in the North Pacific doesn't stay in the North Pacific.
Okay, well, I think we've covered the bad news pretty well. I think we're going to switch to some good news. Yeah, and two pieces. So let's summarize one of the most important climate truths that everyone needs to know. And unfortunately, my experience last week is very few people know it. And I'm talking about people that really should know. And that is that the data, the measured data from satellites is telling us that, and thermometers are telling us that the Earth is warming faster than we thought it would. And there are some scientists, including Jim Hansen, Leon Simons, and their colleagues, who have explained why this is. And it's not that complicated, actually. You can read it and understand it. It's pretty straightforward. There's a number of reasons why this is happening. And one is, and the two basic things are that our estimate of how much the world warms for a given amount of CO2 was wrong. It warms more than we thought. One of the reasons is because there are less clouds when the world gets warmer, and therefore the Earth warms more when the Earth warms up, because there's less clouds, and then the Earth absorbs more sun. That's one. And then also that the effect of cooling from aerosols was more than we thought. And as we clean up those aerosols, we're also getting more warming. So that's the quick answer to the first truth. And it's a very important truth. And it would be really important for the world to understand this, because then you wouldn't have these like ineffectual COP meetings where nothing happens and they don't even want to mention the words fossil fuels, because they're just kind of, everyone's, we should be assuming the worst and hoping for the best, but instead we're assuming the best and allowing the worst to happen. So we got to get the word out on number one. But let's move to number two, because one thing that's very exciting is that the price of solar panels has dropped about 99% in the last 30 years or so. In the last 10 years, the cost of solar power has dropped 80%. The cost of lithium-ion batteries have dropped 90%. And the cost of wind energy has dropped about 60, maybe 65%. And that has made renewable energy the cheapest form of energy, like in the history of the world. And besides the fact that it's inexpensive, the fuel source is the sun and the wind. which are available everywhere for free, unlike gasoline or diesel fuel or natural gas, where you need to buy them from someone. So if you're in a developing, let's say you're in Africa and you're relying on fossil fuels, that means every year some country it's shipping it to you. You're dependent on them, and you're under their thumb basically. And look what happened when the Ukraine war broke out. Europe was all of a sudden in a crisis because they didn't have enough natural gas and things like that. So renewable energy has a lot of benefits besides the fact that it doesn't cause climate change. That's a really big benefit. But it's also less expensive than fossil fuel now for electricity generation already. And there are other uses of fossil fuels for heating, for example, where it's somewhat more of a challenge for electricity generated from renewable energy to perform as cheaply as by the way, when I say cheaply for fossil fuels don't include all their costs. They don't include the fact that they kill 8 million people a year from pollution, that they cause hundreds of billions of dollars in climate damage and trillions in the future. They don't include any of those costs. But I'm talking about the price you pay today for heating is sometimes cheaper. But that is changing as we move to heat pumps, because heat pumps run on electricity and they're 5 times more efficient than a resistive heating type of situation, and therefore they are
have an efficiency of about 300% or often higher, which seems impossible, but they take heat out of the air, so they cool the air outside and they pump the air inside instead of just heating a resistance wire and blowing the air inside your room.
They're basically an air conditioner run in reverse. And what they do is they take heat from the outside air, even when it's freezing cold outside. They still take the heat out of the outside air and bring it into your house as warmth. And they work well, and they're getting cheaper all the time because now they're getting popular and they're scaling up production. I want to give you another example, by the way, of how people think that, the carbon capture we're going to talk about carbon capture in a moment, but like these technologies can't keep getting cheaper. Well, I was just in Washington. At the top of the Washington Monument, the very peak of it is made out of a certain metal that was very rare and very expensive when they built it in the 1800s. And that metal is aluminum.
Yeah.
And today,
aluminum is like
the cheapest metal. My computer is made out of aluminum here. Everything's made out of airplanes are made out of aluminum. Vast quantities of aluminum, and it's because we figured out how to make these things more efficiently than back then when it was a very expensive, complex process.
It's especially because we found a lot of very cheap energy, right? And it takes a lot of energy to take aluminum out of bauxite.
Yeah,
bauxite, whatever you pronounce it as in English. But I just want to go back a bit because why I also want to highlight this point is also because for example, Bill Gates in his letter, he also had like 3 points, and one of the points was also about about what I already mentioned about the need for global development and to save poor people from dying and from poverty. And he focuses a lot on these certain diseases like malaria and measles, and which are of course you can like sell vaccines. You can those are quite relatively easy things to solve, which you can also like invest in and make money with. But if you look at the developing countries where in Africa over 1 billion people still depend on using biomass for cooking their food.
Wood, dried cow dung.
Cow dung. I spent over 10 years working in Ethiopia, and I spent a lot of time in these huts filled with this smoke from burning cow dung, right? And then it's like extremely smelly.
Well, all the time. I mean, it kills a lot of people.
And to me, that's like, of course, I'm exposed to it like a few minutes, but these women are inside these rooms like sometimes for 24 hours. And it might sound extreme, but that's their work shift. Like they work one day and then they don't work the next day, and they work that, and they bake these flatbreads in Ethiopia, and then they spend like 20 to 24 hours inside these smoky rooms, and the smoke kills like globally 4 million people. Indoor air pollution. We did a lot of research on this, and we really work on reducing these exposed to these health impacts. But it's often it's more affordable if you look at the whole value chain of them buying the wood, especially if they buy the wood, of course, but also if you value their time and if you value their health. But even if they would just like buy the wood, it's so much more affordable to use clean energy, right? To use electricity, hydropower, solar power, wind power, whatever. Then and you could have all these benefits. So it's to me, it's really crazy that we live in 2025, and people like Bill Gates, who talk about health and about poverty all the time, they barely ever mention these 4 million people globally dying every year from indoor air pollution, which is more than malaria, tuberculosis, HIV combined. Right? It's such an enormous, and it could help these people, of course, to if you lift them out of poverty. They get opportunity cost. They can spend time instead of collecting firewood, and instead of spending time handling the fire and etc. They can spend it on their family, or they can spend it on work and adding value to their community. So there's so much.
Actually, just the wealth of
and of course, then to finish up, the technology is there already, right? These solar panels are there. They are affordable. They can be invested in, and or other technologies, right? It's criminal that the existing technologies like nuclear was not allowed to be deployed in developing countries under the Clean Development Mechanism because of some old-fashioned fear from the 70s, right? So the technology has existed. But still, Africa has less solar panels installed than the Netherlands, right? It's really crazy to me why these, as we call the clean and affordable technology that can lift billions out of poverty, is not reaching those people yet.
I think that's two things about Bill Gates. One is his wealth alone could fund the panels and the battery you need and the induction cooktop for probably 100 million people. That one. His wealth alone of one person could probably fund that. But he doesn't even have to. People.
He doesn't have to give it. Like they don't want handouts, right? I think that's important to mention. The people in Africa, right? They are proud people. They work hard. They are like. Of course, there's lazy people there, but there's lazy people everywhere, right? It's like this image people have of Africa is like completely ridiculous, based on this Life Aid bullshit, right? Where the clinging chains of doom and these songs that have like created a narrative about Africa, which is completely wrong. These the people want to invest. They want to get access to these technologies that help them, that make their lives more convenient, but they just don't have the access because they are left out. Because we don't see them as a market. We don't see them as a like we bring aid, but we don't bring like trade, right? And they need investments. That's really what they need, and then they can grow, and they can grow really sustainably, right? Ethiopia, for example, they don't allow fossil fuel cars anymore. They only allow electric cars. Right? They have electricity, as you mentioned. They don't want to import fossil fuels, which they don't have. Because that's really bad for their exchange rates, and they want clean air, so they only allow new cars. They should be electric, and they are producing them now more and more locally as well.
Okay. The other point I want to make about Bill Gates is that, and I said this long ago because I actually met him like in 2009 or 10 or something, and back then he was saying that climate change is not a problem. We have to solve malaria, and I go, the good news about climate change is if you don't address it, you won't have to worry about malaria because there's not going to be anyone around. He then talked to some climate scientists and got a little bit of climate change religion, realized it was a very serious problem, did some things in that area. But now he's getting, and we've talked about in this program, I mean, some people think that climate change is going to cause a 3% drop in GDP by 2100 because somebody got a Nobel Prize for saying that. And it's the most absurd thing you could ever imagine. So there's some people like, and I think Bill is one of them, who believes that climate change won't have serious impacts, but he's wrong, unfortunately. So let's get to the last truth, which is a very positive. Well, it's both a positive and negative truth. The good news is there is so much we could do if we chose to succeed. As Kevin Anderson said on this program, like, we're choosing to fail on climate change. We don't have to keep increasing fossil fuels. We have the technology, as we just talked about. It would be cheaper, if we actually switched to renewables, and we would save millions of lives. We've saved trillions of dollars. We could do it. We're just choosing not to do it. But let's talk about a world in which we choose to succeed. In that world, we choose to phase out fossil fuels. We don't just subsidize renewables. We give a timeline for phasing them out. First thing we would do is phase out fossil fuel cars, which we're doing kind of anyway. The market is doing it, but we could do it on a faster trajectory. We could say by 2035, fossil fuel. You could even say 2030, by the way. We could then say no more fossil fuel electricity generation, because renewables are great at making electricity. They do that really well. They do it cheaper than fossil fuels. And yet these coal plants and natural gas plants are paid for, and the investors want to make their money on them, so they don't want to shut them down, even if there are cheaper alternatives. So we have to help them on their way by passing laws that say that you have to phase out these things and finish up, I would say, by 2035, certainly no later than 2040, and get rid of all the electricity. And then the last thing is heating and industrial process heat from fossil fuels. And that, again, with heat pumps, industrial heat pumps, which is a separate thing, and arc furnaces and all these kind of things, there are ways of doing it. And the way to make it happen is by not allowing the use of fossil fuels after a certain date. And it's not like a cutoff. You have to, it's a line that comes down. We can do that. That's step one. Now, the problem is, and this is the part I think a lot of people don't understand, if we totally cut our fossil fuel use to zero, but let's say by 2050, which we're not going to do, by the way, but let's just say we did it, things would not get better. In fact, they will continue to get worse. Sea level rise will continue to go up for centuries and millennia, because the last time CO2 levels were this high, sea levels were 75 feet higher than they are now. And that's where we're headed, even if we stopped emissions. So I want to get this by that we are past the point now. If we're really, really lucky, and I don't think we actually would be lucky, temperatures would stop rising when we hit zero emissions. But their earth feedbacks, the cloud thing we talked about, that probably would continue to go up for a while. That theory that temperatures stop when we stop emitting is based on optimistic assumptions. But
and only CO2. That's really there's big uncertainty there, and they pretend it's many of these studies, they pretend like other greenhouse gases and aerosols don't exist.
Right. But they also go to zero. Right. They also go to zero. That's what
aerosols are, of course, coupled to the CO2 emissions, as I showed you clearly with these two graphs, right? It's like,
yeah. No, the aerosols would go away, and that would warm the earth. But that would also, they're also assuming methane goes away, and that would cool the earth.
Sometimes they are, but sometimes they are pretending it's just CO2. Let's not and of course, people, as long as there's people, they will keep eating rice, they will keep producing trash, they will keep having cattle for at least for a while. Right? I don't see
permafrost might start giving off a lot of methane all on its own that they don't assume in their models there.
Of course, yeah.
So the bottom line is, if you're going to assume that temperatures will stabilize, and by the way, they're going to stabilize not at where they are now. They're going to stabilize at where they are in the future, which, like in 2050, would be, let's say, 2.5 degrees, and that's in an optimistic scenario. But 2.5 degrees, that's really bad. But even if you're assuming that, I think of Clint Eastwood saying, "Are you feeling lucky, punk?" You know. So, this is not. If that's your plan, which, by the way, that is the world plan, the IPCC, United Nations, the plan. Well, they do assume, by the way, there's going to be some carbon dioxide removal because their math doesn't work without it. But they're assuming we're just going to lower emissions down to zero in 2050, even though we're not starting now. We'll start soon. We're not going to get rid of we're not going to talk about fossil fuels for now, but someday we will. I mean, it's kind of ridiculous. But let's say we did that and they assume some carbon dioxide removal, which is the next step. So emissions reduction alone will not keep a safe climate for our children, period. End of story. There are no scenarios that are realistic. Yes, you could cut it to zero tomorrow, maybe, and maybe it would work. But we're not cutting it tomorrow to zero, and we can't. So step two is we do have to remove the trillion tons that are up there, the extra trillion tons. And to do that, we actually have to remove 2.5 trillion tons, because as we remove CO2 from the atmosphere, the ocean balance will send it back up, the part that it absorbed. And so we have a lot of work to do there. The bad news is that it's very expensive today to do it. There's many different ways to do it. There's mechanical machines filters that can suck CO2 out of the air. There's you can crush certain kinds of rock and just lay it on the beach, and that will absorb CO2. There's a lot of ideas, and they all vary in cost, but some of them are as high as $1,000 a ton. Some of them claim to be under $100 a ton. But the good news, just like aluminum on the top of the Washington Monument, if there was a big market for this, people would figure out how to lower the cost. And right now, there's very little of this being done, because the bottom line is no one's really paying for it except a little bit. Some voluntary markets exist that pay for some of it. Government does a little subsidies here and there for it as well. But if we ever got serious about it, then the government would pay for it and at scale, and then we would have a lot of it, and it would actually be cheap. Nowhere near as cheap as not putting it up in the first place, by the way. Still extremely expensive, on the order of trillions of dollars a year, but that would be cheaper than not doing it, because not doing it.
There's a lot of disclaimers here. I think that's the point. Is it's still possible to avoid the worst climate impacts, but there's a lot of disclaimers, like we're not doing it. But I think one thing we haven't talked about yet is also adaptation, right? And of course, you can talk about sunlight reflection methods to cool things down, or keep it from warming further. But I think the first thing also we really have to look at, because there is mitigation, but even the first time I was in Ethiopia, I think that was like, I don't even remember the year. I think 2012, 2011, when the people from these African countries where we were at this climate conference, they were saying, so these Western countries, so from the Netherlands and all these donor countries, we're talking about mitigation, and then the people from these developing countries, from Africa mainly, they were all talking about adaptation, because they are already facing a climate that is very hot, that is warming faster, and is also facing a lot of deforestation, and deforestation also changes the regional climate. So adaptation is crucial, and that's also when I learned that if you want to stabilize the regional climate, it's also crucial to grow trees, to grow regional trees that stabilize regional climate by, if you sit under a tree, I think at a very small scale, if you just sit under a tree, that you have shade, and that the tree is glowing and using that energy, and it's evaporating water, and it creates this regional microclimate, right? And the same happens in a forest on a larger level, and the same happens in a country on a large level, where you just these ecosystems. If you restore ecosystems, they can really create a more stable climate. And I think that's also what we really need to do, not just native species, but also looking at crops, for example, because a big risk the coming decades will be growing food.
And right, but there is a limit to adaptation. For example, there's rain.
Of course, there's a limit to adaptation. So I'm not. Of course, we fully agree on that. So we can, but the impacts. If we talk about climate impacts, that's also very much about adapting to the changes that are still unavoidable, right? So if you want to reduce the impacts in your country, you need to be able to be aware of the real changes that are happening, the rate of change, especially regionally, as I showed you, and then adapt to that change, which is now unavoidable, right? Because we cannot avoid all climate change. It's not that we can avoid all the changes. We will reach 2 degrees almost certainly, right? Because I don't see the greenhouse gas emissions like going down extremely fast and cooling happening, intentional cooling happening. I cannot see that happening in the next decade. So we will hit 2 degrees. So, but when that happens, and as that is happening, and if as the impact is much stronger in the region where we're cooling the most unintentionally, and we've cleaned up this air pollution, we really have to be aware of these rapid changes that are coming and try to adapt as much as we can.
Right, but the problem is, though, if we do that, then we don't get to the third thing. Is if we just do adaptation. By the way, I should point out that emissions reduction, as we talked about, even if you do it, temperature doesn't come down. It will stop going up as fast, and if you're really, really lucky, it might level off. With carbon removal, the temperature could end up going down, only if, by the way, you're already at zero emissions, because otherwise you're just offsetting your emissions and you're not really lowering the CO2 content of the atmosphere. But if you do that, temperature will go down. But this is a very long process because there's so much up there. So even if we removed it as fast as we currently put it up, it would only be removing it by about 2% a year. So it would take many decades before the temperature would start to really go down in a noticeable way. So there is one more thing we can do, and then, by the way, if it gets to 2 and 3 degrees, let's say 3 degrees at 2050, this adaptation thing is out the window. I mean, the people will not be adapting to half meter in 24-hour rainfall, which is already happening in some places. There's no infrastructure on Earth that's handling that kind of thing, or a meter in some cases. Insane. The fires we've seen, we can do better on building buildings and things. Tehran running out of water. Okay, so yeah, the adaptation for that is building a new city somewhere else, right? So we're not going to be. I mean, individuals will not be adapting to what's going on if we let it get so out of hand that it's difficult for civilization or organized governments to operate, right? So there is one more thing we can do, and it turns out it's really cheap, relatively speaking, with an order of billions of dollars a year instead of trillions. And that is what's called sunlight reflection methods, solar radiation management, solar geoengineering. Very controversial. We've been talking about it on the show recently too, in some controversies. People don't like it because they think it's screwing around with the climate. I just suggest to them that maybe they should have thought about that 200 years ago when we started screwing around with the climate. And will it have negative side effects? Yeah, there'll be some negative side effects, although we know they're not going to be really terrible, because this thing happens on its own naturally a few times a century when there's a very large volcano. And actually, as someone in the questions noted, hey, when that volcano at Mount Pinatubo happened, it actually caused the line to be less permanently of CO2 going up. And that's because when you cool the earth, you actually get less emissions from the earth, and you actually lower the increase in CO2 every year. So there's a lot of other things that happen. But the most important thing is you stop the temperature from getting out of control. And again, we don't know enough how to do it exactly right today, but the technology is not really a problem. It's just having the knowledge of the best way to do it, when to do it, where to do it, and all that kind of thing. But we do know it will work because volcanoes do it.
Right? To get the technology ready will take 10 years. I think that's what we should be clear about that as well, right? It's not a silver bullet. It will not. It can reduce the impact, but it's the technology. We often talk about it like the technology is there, right? But except for some guys playing with balloons, there's not a lot of anthropogenic emissions, and that's of course also not like a negligible amount. There's there's negligible amounts of anthropogenic aerosols entering the stratosphere, right? So, and of course there's some investments happening. I think it's I still have to look into that. It's called this company startup. It's called Stardust. I think they've invested 60 million, so they want to do some pilots, but still you do need billions. Right?
Yeah, you need billions, but you don't need trillions. That's my point.
No, of course but
keep in mind, we're not really doing this seriously yet. There's very, very little funding for this, even that one company. But the academic funding for this is trivial, probably compared to what's spent on researching tomatoes or something like that. So
you don't know how much we are spending on researching tomatoes in the Netherlands.
Probably a lot, right?
Yeah.
So we're not. But my point is, this is what happens when we finally choose to succeed, which we haven't done yet. We haven't chosen to succeed. We're choosing to fail. We're choosing to continue emitting like crazy. We're not taking carbon capture seriously. We're doing a little bit. There's some experiments. It's kind of, first of a kind experiments and demonstrations happening, and they work, but they're expensive. It's just like if you built a prototype car, that car is going to cost a hell of a lot more than the production car. And anyway, so we could do that seriously, and we could be researching the hell out of solar geoengineering so that we have it as an emergency thing if we need it, which I'm pretty sure we're going to need it at this point. In fact, I guarantee we're going to use it because we're not doing anything else effectively. When things get so bad that the politicians' only choice to provide relief. Remember, solar geoengineering provides, once you do it, the cooling starts within like a month or two. Unlike carbon capture, where the cooling starts in half a century or so, so it's a very different timeline. And so the only politically acceptable timeline, I think, is going to be geoengineering. And again, people don't like it. And then one of the number one reasons they don't like it is they think it's going to give social license to fossil fuel companies to continue doing what they're doing. So, it's not as hot anymore, so we can still make fossil fuels. That is one possible outcome. But then again, that is also still choosing to fail. Yeah, and that's asking those companies to pretty please lower your emissions rather than telling them they have to lower their emissions and cut them to zero eventually.
Yeah, the point is,
if we're serious, we'll do the latter. If we're not serious, we'll do the former.
The point is also that we don't take it serious because we don't know how bad it is, and that's what aerosols have been doing for years, for centuries even. Hiding the real impact of our greenhouse gases, and I think that's
you're supporting the line that people are worried that geoengineering we're doing geoengineering, so it's accidental geoengineering, but purposeful geoengineering would allow us to continue on our harmful ways. But again, we have all the information, so we can make the choice to succeed or fail. And I have to say it again, by the way, and I didn't say it maybe today. If we continue to choose to fail, we will.
You said it.
It's very clear that the path we are on leads to failure. The good news is there's no reason we have to stay on that path.
But the answer to that is also like, if we don't know how bad it really is,
then I agree with that.
It is much more likely that we don't think we really are failing, so we don't really have to do much, right?
I agree with that.
So because that's really the point. So, and of course, like if you really think, if you realize, and I do think that's the case, that if we really want to reduce the rate of warming, and we want to keep the AMOC from slowing down, with the we need to do that this decade. Yeah. We will need to do that this decade, right? And the only technology that's ready is allowing ships to emit sulfur from outside on the open ocean, where already algae are emitting some, and it doesn't impact health that much. You know, that's the rational, technical answer to this question. But then, like, to me, like one of the most important reasons not to do that, like the most also in a way rational reason to do it, which is also like in a way very wrong, is because if we don't do it, the climate impacts over the next decade will be so severe that it might shock people into action. And I don't know if that's true, but that's of course a very, like, yeah, you don't really want that to be true, but in a way it's, you know, we do see that once the shit
Pearl Harbor theory,
people start to realize how bad it can get, right? Then there's many examples where, and there's also some examples against it, but there's many examples where people come together and then they start to act once they see how bad it really gets. And yeah, unfortunately, I think we do need some big impacts, and I hope it won't be too big. But yeah.
Well, we've had, I mean, yeah. Well, again, the other thing to know is that we're not rational beings. We think of ourselves as rational beings, but we're obviously not, and we're not being rational about this whatsoever. But one way you can help is by liking and subscribing, because then how bad it really is will be spread to more people, and maybe it'll reach just those few people that need to know more. Or anyway, you can do your part. And with that, let's bring Stacy in here, because it's been a
3
long time
years.
of discussion. You can leave Leon and I in a room, and we'll just talk forever here.
Sorry, Stacy.
Hi guys, I have so many questions racked up. I don't even have any of my own, except for to rephrase one of Frosty's comments into one.
Okay.
With all of the reinforcing feedbacks or tipping points being discovered, do you think it is possible to ever see real cooling again?
Sure.
Yeah.
Well, I mean, we just talked about it. I mean, if we did geoengineering, I mean, we know we can do it, and we know it works.
Oh, okay. All right. Well, I guess
if you see a super volcano, like, in a way that's the same, right? If you have a strong volcano. Sorry?
I guess I was interpreting it as without solar geoengineering. Is it possible? Like, if we just cut fossil fuel emissions, we have so much baked in. Well,
no, again, I want to make, this is a really important point. Everyone, you know, I don't know what the number is, but it has to be at least 90% of the population has a model in their head of what pollution is. That model is, it's a bad thing, and when you stop doing it, it gets better. Water pollution, air pollution, every bad thing we do. Like maybe if there's another problem with guns, gun deaths, we get rid of guns, you know, the deaths go down after that, right? That is not climate change. That is not CO2. CO2 does not get better when you finally stop emitting it. It only if you're really lucky, and we're probably not going to be lucky, it won't get worse, but it won't get better. So the answer for cooling,
for a couple thousand years,
a possibility.
For a couple thousand years.
Oh yeah, for thousands of years. Now in 10,000. By the way, the number I saw was you had most of the warming for the next 1,000 years, and like 80% of it for the next 10,000 years. So you know, just forget it. It's forever. Okay, as far as we're concerned. And yeah, the Earth will be fine. By the way,
But before that, before that comes the question whether we can reduce emissions, right? And I think that's even that seems like a easy question to answer, but can we really do that? Right? If you look at the COVID pandemic, and like most planes stopped flying, most people stopped driving to work, but what was those are in a way relatively like easy steps, right? Because it's relatively easy to do that. But the impact was only 7% or so from CO2 emissions going down.
We continued to heat our homes. We continued to run factories.
Of course, and of course we can make steps with that as well. But still, the biggest steps, like if you would do like the biggest step, like what everyone says, we should stop flying, we should stop driving to work and work from home and whatever. Like in a way, we did that already, and we had that test.
No. Just stop.
Right?
Pause. I need to clarify one thing. It isn't about stopping moving. It isn't about not going places or whatever. It's doing it in a way that has the least amount of impact, and that is
for sure.
walking, biking, transit. You can do it.
But we stopped doing it.
You can't do it depending where you live, though. I mean, you know, we built suburbs because we had cars, and now those suburbs are these isolated homes that are very far from the shopping or visiting other people and things like that. But
you did.
I think that what I would say, it's not going to happen on its own. Renewable energy is cheaper than fossil fuels, and it will eventually just replace fossil fuels for economic reasons, no matter what the fossil fuel companies say. That will happen, but it's not going to happen in a time frame that's going to be good enough for us to protect ourselves. So we could have policies, and then I really have to emphasize this. There's like hoping that things happen. It's waiting for the price to drop. It's all that. Okay, there might be a positive eventual trajectory that way, but with policy, you can force things to happen. You can phase out fossil fuels, and then instead of 100% of renewable energy so far going only to supply new energy demand, rather than replacing fossil fuels, because fossil fuels are at a record high. If you had a policy where you had to phase out fossil fuels, then those renewables would go to immediately replacing the fossil fuels, right? Because it would be less energy from the fossil fuels. You'd have to fill it in, and you'd fill it in with renewables. And we would actually do that. Getting rid of cars that emit emission, CO2, you can do that. You can do it very rapidly now. The EVs are cheaper than fossil fuel cars, like in China, where it's over 50% of all new sales are EVs, right? And solar power. Anyway, we've talked about that. So all that's possible. It's also possible the only way to lower the temperature without geoengineering is with carbon dioxide removal, taking CO2 out of the atmosphere. You can do that, but again, we're talking about many decades before you'd notice it. Whereas with geoengineering, you'd notice it next month. It would be first of all, we're not going to turn it on to full blast. We're going to start with a very little bit. We'll lower the temperature by 0.1 degree, and we'll see how that goes and how it's working. And then we'll do another 0.1, and that kind of thing. But you could get to a degree of cooling in, a couple of years kind of time frame. Once, as Leon said, once you have it worked out. In the meantime, if you just turned off that International Maritime Organization regulation that lowered the shipping emissions, and you turn that back on, you'd get 0.2 degrees of cooling right away. So that's how much warming it causes.
So
within a few years.
Jeffrey had a question about that, about the IMO.
Okay, so go ahead. Let's go to the questions. And
let's
let Eli in on that.
Oh,
and before we go to those, Eli, welcome. And what's your comment or question?
Thanks. A couple of comments. The first, talking about 3C by 20 is an irreal scenario in that before we get there, we've gotten to C, 1 and 3 of C, at which million people are living in places that are at risk of at least one lethal wet bulb event per decade. And at 2C, that gets to 1 billion people experiencing at least one lethal wet bulb event per decade. And at 3C, that goes to 3 billion people. And I think that even if the 2C lethal wet bulb off 1 billion people, the other 2 billion would not sit around and wait for it to come to them without saying, yeah, we need some solar radiation management. So the question is not if we do solar radiation management. It's rather when we face reality and get serious about it, and how. And I don't disagree with Leon that switching back to the higher sulfur is a good near-term measure, but there are also other near for solar radiation. In particular, it doesn't everywhere. Green cloud brightening, that doesn't take a year, that doesn't take months, that cools the temperature immediately, right?
Yeah, but is the technology ready, right? Of course, I understand.
Well, okay, yes.
Sorry.
Yes, I agree but that's already being tested in Australia, and it should be tested as well in the not distant.
Yeah,
so,
but it's very different from these 50,000 ships burning these what is it, millions of tons of fuel, and put it in the atmosphere. Like hundreds of millions of tons of fuel are being burned, and that's really an enormous scale. The scale of these sulfur emissions and the spread it cannot be overstated, right? It's really enormous. So yeah, you cannot like build a water cannon and hope that it will do the same. It's yeah, it takes a lot of time and investments to get something to work at a similar level.
Well, I think that
ships were doing for free, right?
Okay, in this, extrapolating from where we are, negligible R&D is going into it. Yes, you're absolutely right. My point is that to get serious about that R&D, and the cloud brightening is probably the lowest cost per intervention that we can build by. It will be surprising to people. Space-based, so when that's done at scale with the economies of scale in an optimized way, and the advantage of that having other impacts on atmospheric chemistry. And additionally, sulfate is what everybody talks about, is because it's the example we have because of volcanoes and shipping emissions, or emissions in general, fossil emissions in general. But there are other options that are either more benign or possibly even beneficial. So this is a huge area where there is so much room to do so much better.
Sure. Okay, but I think we agree there. But again, I might make the point: we can choose to succeed, and then if choosing to succeed includes researching that and getting it all worked out as fast as we can. Right now, we're not. And we're talking about it on this program because of a number of things. One is the warming is worse than people think, so they're not as incentivized to act as they should be. But once they understand, they're seeing the impacts, they don't understand what 2 degrees in 2030 means, or 3 degrees in 2050, 2060 means. And that is catastrophic, totally unacceptable. And if we start working on geoengineering in 2050, then we're pretty much screwed. So we got to get started on it.
Yes, and the fact that if we discussed recently, crossed 2C time in the middle of the 2030s. That's a billion people risk of lethal condition at least once a decade. Much more serious than people are really grasping, and that's leaving other misery and unpleasantness that would face us. We really
don't worry. COP30 is taking care of all of it. Oh, actually, no. Sorry. Okay. Let's Stacy. What are some of the questions?
Oh my gosh. Okay, so what I was going to say, so Jeffrey had mentioned something about the IMO 2020 regulation. He said it caused 0.2 C degrees of warming to date, and there is only 0.1 C remaining from the shipping aerosol change.
Mm-hmm.
Why would we expect the rate of warming from the last 5 years to continue?
That's a good question, and that's because it doesn't work like that. Because and this applies to all. By the way, I think is fascinating. I kind of learned this by reading Jim's papers and things like that. But Jim Hansen's papers. So you think that you do something and it causes warming. No, you do something and it causes warming, which causes more warming. In other words, there are feedback. So you do the initial thing, the initial push, and then that causes feedback. So when Jim and Leon and everyone says that ECS, equilibrium climate sensitivity, is 4.5 degrees Celsius for a doubling of CO2, you think, oh, I double CO2 and then all of a sudden it's 4.5 degrees warmer. No. You double, let's say we just did an experiment on Earth and one day we just doubled CO2. In 10 years, we would see about 1.5 degrees of warming. In 100 years, we would see a total of 3 degrees of warming, or another 1.5 over the next 90, 100 years. And then in 1,000 years, we would see 4.5 degrees of warming. So
I think this question is not about that.
Well, it is, because the shipping change happened and it changed.
Yeah, sure.
And as Jim pointed out, he said this year was going to be warm because of the shipping change from a long time ago, because ECS is playing out, right? We got that initial jolt, and now we're going to see the warming that comes from it.
But I think it's about like the next 25 years, right? So
well, you get most of it in the first 10, right? A third of it in the 10.
Exactly. So then you would expect, if that is true, you would expect it to stabilize. Or the rate of warming to go back to, and depending, of course, very much on the greenhouse gas emissions and the further aerosol reduction, etc. But personally, I don't know. I think that the honest question always is I don't know, because we don't know what will happen in the future. But I very much think that this rate will continue, because the main heat sink is the oceans, and the forcing change is only over the oceans, and it takes a lot of heat to heat the oceans, and the cloud feedback is also mainly over the oceans, especially over the North Pacific, and you see it still increasing. You see this net flux still increasing, especially over the North Pacific, but also in other regions. So we don't see any we don't see any indication of the rate decreasing. We only see, especially regionally, right? I think, and I cannot stress this enough, is really the regional impacts are very much much more important to most than the global average. So, and then you see this imbalance keep increasing. So I don't know what that will stop. That's the honest answer, right? I showed you the specific decadal oscillation. Like, we don't know what the effect of these aerosol changes is on this specific decadal oscillation. If it goes up, everyone was thinking, if this PDO is positive, the imbalance is higher. But it has been negative for 5 years, and the imbalance has been record high. So if it goes back up, it could increase further, right? So we have this natural variability, and this aerosol forcing could be even stronger than we thought, right? It could be, because we saw the best estimate, or based on the only limited amount of years. We only had one El Nino. We have only had a negative PDO, and and we don't know. We've never been here before, right? We've returning to a climate that hasn't existed for 120,000 years, and we'll soon reach a climate that hasn't happened in the millions of years, maybe not ever, right? If you take everything into account. So the honest answer is we don't know, and it could change very, very fast, and the rate of warming could increase further, right? And that's why, like, we cannot exclude it. That's maybe the chance is not 50%, maybe it's 50-50, I don't know. But again, that doesn't really matter. We really have to assume that it will happen.
And again, warming causes warming. So, for example, the CO2 per year increase is going up as the Earth warms. And then, so you could stop doing whatever, your shipping thing or whatever it was that was releasing sulfur or CO2 for that matter. And the Earth just decides, hey, I'm going to release methane from the shallow clathrates in the Arctic Ocean or the melting permafrost or anything like that. And hell with you guys. I'm going to get in on this game of increasing emissions. And so
I think it will be very hard to reduce emissions faster than the rate of atmospheric increase is growing, right? The rate of, because of the nature used to absorb about 50%, 40 to 50% of our emissions, and about half of that was from the biosphere and half by the oceans. But the biosphere is decreasing. So yeah, we reach temperatures, especially when within 10 years when the El Nino is permanent, right? The global temperature is like a peak now, right? In 5 or 10 years, we'll reach that level where a 1.6 or 7 degrees Celsius year is now then the average, or even faster, right? So, and then how much CO2 will the biosphere absorb for us? Maybe not so much anymore, like it did last year.
As the oceans heat up, they hold less CO2, and a lot of other things like that are happening. So, okay, let's move on to the next one because we could.
Okay, you had mentioned El Nino or La Nina, I'm not sure. But Jean wants to know, is there any information about future El Nino and La Nina patterns? Will it simply stop shifting when the ocean gets hotter?
No, we expect it to keep the cycle will continue, and of course it might not. I think that there are some indications, and I'm not an expert on this, that there's some shifts, but I don't think there will be no cycle anymore. But for the North Atlantic, like the North, I think there's North Atlantic oscillation and Pacific Decadal oscillation, those are very much also forcing driven, especially also aerosol forcing driven. So that's what we are learning now, that it might have been, because you could look back and you can see, for example, from ocean data records from these drill cores, you can see that there's also these fluctuations, but that can also be just because of aerosols, right? Because of natural air pollution and because of anthropogenic air pollution, and that has also caused these ocean currents to be impacted. So yeah, it's I think that I do of course there will always be natural variability, right? There's always a cycle and there's always some fluctuation. It happens everywhere. Even if you aim your thermal camera on your coffee, you can see these different heating patterns inside your coffee. So I think it's inherent of a system, especially one that's always heated from different parts of the globe. And yeah,
but I think it's important to note though that it's going to be El Nino is warmer and La Nina is cooler, but that's on top of a totally warming ocean to start with. So yes, it's going to go up and down, this natural variability, but it's laid upon a steadily increasing temperature for the ocean. All right. What's
Yeah.
what else you have? there?
Okay. Martin asked this early on. He said, something occurred to me recently. All damage assessments and studies based on AR6 are probably too optimistic. Specifically, UK actuaries at 4 billion plus dead at 3 degrees, and Allianz, sorry, adaptation is impossible after 3 degrees.
Yeah. So the answer is, well, yeah. First of all, the AR6, as we're pointing out, is optimistic about what the warming is going to be. And although when you really look at the chart, Leon showed, there's all over the place. But if you're being conservative, as you should be, assume the worst, hope for the best, and plan for 3 degrees by 2050 rather than 1.5, which we're already at 1.5. So so the AR6 is optimistic to start with, and the next part of this is people are not being realistic about what these numbers mean. 2 degrees doesn't sound like. First of all, people think 2 degrees is safe because that was the number, the plan not to go over it. The implication being, well, if that's the number we're saying we shouldn't go over, that must be an okay number to reach. And unfortunately, that's wrong. I mean, maybe when it first came up 20, 30 years ago, 2 degrees was thought of as maybe, it was thought of as being the border between safe and dangerous climate change. Now it's viewed as the border between dangerous and very dangerous climate change.
Well, and actually, that's a good time to insert what Nevitz brought up just recently. You might be able to find it. Our biggest problem is education and the massive lack of it. When people hear 1.5 to 3 degrees Celsius, they will simply think, when I leave my house, I lower the temperature by that much. No big deal. And they're totally right.
That's right. But if you can even go outside and it's 5 degrees warmer when you leave the house, right? And that's fine if you do that. If your body temperature goes up 5 degrees, you're dead. So think of it more like the temperature of the earth is measuring like your body temperature. And
You're
you
not
go up
dead
2
if
degrees.
it goes up 5 degrees.
Yeah,
You'll die.
Yeah. Well,
And stay
5
there.
degrees Celsius, you're way dead. 5
Oh.
degrees
You're saying if
Fahrenheit.
it
I
doesn't-
actually
it's
had a 5-degree
103.
Fahrenheit increase, and I was in the hospital.
103.6?
I went. Well, I had 105 once. I was in the hospital. So
Well,
yeah.
that's
But I was talking about Celsius.
6
Celsius, you're dead.
something.
Yeah, let's talk about Celsius here.
I know
With
Americans
science,
only
you
do
know.
Fahrenheit. Okay, 10 degrees. You go out 10 degrees warmer.
Yeah,
one day.
I'll agree with that. Okay.
I'm not listening to you.
Okay, so
Okay.
yeah.
There's so many more. One Reese asked early on, where
do a
does
quick,
you want that one?
Which one?
No,
Go
I'm
ahead.
not doing that.
Do you want that one?
Oh no, I'm sorry. Did I hit one that I didn't mean to do that?
Yeah.
I'm sorry.
Okay.
I don't know what I'm doing there.
Reese asked early on, where does your analysis sit in terms of acceptance among climate scientists? For example, ECS is 4 degrees Celsius plus. Most agree or still see this as possible, but unlikely.
That's a very good question, by the way. Sort of the question of the hour, and one that Jim Hansen is writing about, saying that it's not being covered for a lot of reasons. And it's hard to understand why. Again, scientists disagree with Jim and Leon, for that matter. But they don't I haven't seen yet where they disagree about the science. Like they say,
Yeah.
oh, the series data is wrong. Or, oh, no, you did the
Yeah,
calculation
indeed, like-
wrong. Or you did that right. Calculations are really simple, by the way. You can follow them yourself. It's not like some really complicated thing. And so I haven't seen scientists disagree with the science. They just
They disagree
oh, it's
with
an
the
outlier.
narrative.
It's an-
They disagree with the narrative that's resulting from the science. So many don't. Many like and it, yeah. So it's off. It's a bit of a loaded question, right? So
Right.
it's very much in a way you're saying like the IPCC is wrong. Even just saying that the IPCC, if you just say that, people are hurt. Especially
a lot of
like
people.
those scientists spend a lot of their free time working on it, and they are. It's a respected organization, and they are proud to have done that. And and people rely on it, and they want to trust it. They want to be able to trust the science, right?
Oh.
And then if you say the IPCC is wrong, it hurts them. Sometimes they feel it, right? But if you understand the
It's
process,
bad vibes.
sorry,
It's bad vibes.
it's bad vibe. But then if you understand the process, it's the governments that decide what is being said, right? So, for example, some IPCC people who worked at the IPCC, they reached out to me and they said, what happened is that they took, like in the AR6, like the first working group report from the IPCC of the AR6 work group 1, in the summary for policymakers, in the draft it said, early 2030 we will reach 1.5 degrees Celsius, and in the high emission scenario, even before 2030. They scrapped it all, right? They scrapped it all. So they were like, and that's just like one simple example. It's like they keep the information from the policymakers and from the media, because nobody's going to read all those 3,000 pages and try to understand the science. They read the summary, and the summary of the summary. And if you take away the important stuff that we will cross 1.5 in around 2030, and then even we've already crossed it. So because it didn't take into account all this desulfurization of these coal plants in the shipping, but we've talked about it. Then we are kept blind. People are, and that's happening on all these levels, right? So, and the same is happening with the climate sensitivity, right? It's not just us saying this. It's many documents, many recent articles showing it. And if you do a thorough assessment, not just take the average of all these models, but if you do a thorough assessment of what's the most likely based on the evidence, right? That, to me, that's important. I don't care about consensus. I care about what the data tells me. And if someone, even if it is one person, like whoever it is, can explain based on the evidence, can explain that it's higher or lower, and it can explain. And I believe that, right? That's the answer. But if you have to prove it, and I think we did quite a good job at proving it based on paleoclimate, based on modeling, based on the aerosols, based on NASA satellite data, based on all these other lines of evidence, ocean heat column data. We took it all and based our assessment on that. And like, I haven't seen anyone like pick it apart based on the evidence provided.
By the way, I realize one thing we should do is we should have more Ask Me Anything kind of sessions, because we're adding a long discussion that Leon and I had on top of now lots of good questions, and now we're over 2 hours. So I think we should just do like one more question and then call it a wrap.
Oh
and
my
then
gosh! How am I supposed to pick? All right. Well,
we'll schedule an Ask Me Anything where we do nothing but go with user comments.
All right. You have to give me two, because they should be easy.
All right.
They should be easy for you, and they're kind of fun. So the one is from from Brittany. What I don't get with this albedo thing, because I almost think I can answer this. As the water vapor content in the atmosphere goes up, shouldn't there be more clouds, thus raising the albedo?
The water vapor content increases, which also means there's more evaporation, because a cloud is condensated water. It's not water vapor, right? It's
droplets.
And if you have less aerosols are condensation nuclei. So condensation means if you exhale to a window, cold window, you see the water vapor from your air, from the air you blew against the window. You see it condensate against the window. That's also what happens in the atmosphere with these particles. Without these fine aerosol particles, there wouldn't be any clouds. So they are crucial for cloud formation. So if the air warms and you reduce the amount of aerosols in the atmosphere, you will have generally less clouds. Of course, there's some specific, some regional differences, etc. But the current knowledge is that both from decreasing aerosols and from warming, you decrease global cloud cover.
Right. Now, by the way, that wasn't known. Like 20 years ago, we didn't know whether warming would cause more clouds or less clouds. And so, yes, one factor is there's more water vapor in the atmosphere as the temperature warms. That's true. That's one factor of many factors. And the reality of measured satellite data for the last 25 years shows clouds decreasing as the world warms. So that's measured data. Now, things could change, whatever, but that's what we know now, and that accelerates warming. And so, and by the way, it's very warm in the desert. You don't tend to have a lot of clouds
during the day.
During the day, that's right. It's very cold at night too. Anyway, so that's a good question though. But
okay, the last one is just, I think, a fun one. It's from Alpha Ghost. Could we survive underground like in Derinkuyu, which I had to look up, and that is an ancient multi-level underground city in the Cappadocia region of Turkey, built to house up to 20,000 people along with their livestock?
No.
Why?
Well, by the way,
They
the
did for
billionaires are building their bunkers underground. I mean, they'll have some time to enjoy that. We're talking about 8 billion people. You're talking, it's hard to grow food. I guess you could lay solar panels all over the top, I guess. So then you have to come out and dust them off. But, we're talking about, maybe if we started a few hundred years ago and preparing for this, maybe we
Won't the robots do that for us?
probably. So
but you'll be talking
a lot of changes coming, but
what is it, Eli?
You'd also be talking about the worst ecological catastrophes in our imagination, I think. Already we're in the 6th mega extinction event, and that would really just accelerate it far more. Most mammals are out of climates that they are adapted for, right? So
your audio's not that good, Eli. So you gotta work on that. Okay. Anyways, that's a good question. Yeah, can we all go underground and live happily there?
Yeah, go long.
People think we should go to Mars, right?
Go long on caves.
Go long on caves. You can go to Mars.
Yeah.
Remember, living on
in
Mars
the Netherlands,
is much more difficult than living in Antarctica. So, like 100 times more difficult. So,
what is Mars?
Living on Mars, people think that's something we can do. It's like orders of magnitude more difficult than living in Antarctica. So if you just think of living in Antarctica, where like you can't really go out. You can't go out. I mean, the radiation will kill you on Mars. You do have to live underground on Mars, by the way. That's one thing. So we could get into that. There's a lot of reasons why Mars will not work out too well. If that's your plan.
Or Antarctica.
It's one person's plan.
Move 8 billion people to Antarctica.
Yeah. Yeah.
Okay, I think so I've been on for 45 minutes, so I think we can safely call this a cat video now.
All right, there we go. Cat videos. Anyway, thanks everyone for joining us for this long discussion. We will schedule some more like Ask Me Anything so that we only do question answering.
And we could start right away because I have tons here in my notes that go unanswered.
Yeah, save the good ones.
Save the good ones. And then remember to like and subscribe, because we do have to remember to ask for that. It really does help. The algorithm just cares about that. And so if you want more people to see what we're talking about, then please do that. We will see you next Sunday and 10 a.m. Pacific time. Thanks everyone for joining us today and for watching the program later. And
thank you.
We'll see you next time. Thanks, Leon. Thanks, Stacy. Thanks, Eli. Bye, everybody.
See you guys next time.
Bye.